Hi, I'm Zor. Welcome to Zor Education. Today is a little bit unusual lecture. Usually it's all abstract mathematics, etc. Today's lecture is about physics. More precisely about theory of relativity, special theory of relativity. Einstein, many years ago, wrote an article called Electrodynamics, where he basically derived the formulas of special theory of relativity, how coordinates are changing from one system to another, moving relative to the first one. Quite frankly, I didn't understand many of the physical aspects of what he was writing about, and I kind of didn't like the fact that he used a lot of intuitive physical thinking in derivation of his formula. So, as a mathematician, I was thinking about maybe it can be done purely mathematically. Whatever the formulas of special relativity, of transformation of coordinates he could come up with, can it be really just derived very simply? I'm sure many other people did something like this before me, so I do not pretend to be an inventor, discoverer of anything new. But for me, for myself personally, that was something which was new, and I didn't read about this before. I just did it myself, and I was quite satisfied with the results. Now, why I'm basically including this in this particular course? Well, because it's about systems of linear equations. It's a practical implementation of systems of linear equations to a purely physical problem. So my task was, from certain physical aspects, derive system of linear equations, and then basically solve this system to derive the formula of transformation of coordinates. And that's exactly what I'm going to do right now. I will try to be as mathematical as possible. However, there are certain physical aspects, but quite elementary actually, which you would agree with me that even a mathematician can actually accept without any kind of problems. All right, so let me go, and I would like to start from certain principles, certain axioms, if you wish, on which the whole system of equations is built. So the first thing is, what are we talking about? We are talking about the following. Consider we have two systems of coordinates. One and another. So these are upper cases, x and t, and these are lower cases. Now, x represents a space dimension, and t represents time dimension. So, as we know, our physical dimension is basically 3D. We have x, y, and z, and we can add the time parameter, like a fourth dimension. Now, I would like to concentrate on the movements within one particular coordinate, x. It's much easier. To extend it to three-dimensional case is basically purely technical aspect, which I don't want to deal with right now. So let's consider we have a one-dimensional space and a dimension, one extra dimension, which is the time. So this is one system of coordinates. Another system of coordinates is moving relative to the first one with a constant speed of v, as measured in this particular coordinate system. So if you are an observer sitting here, this particular coordinate is moving with the permanent with a constant speed v. Okay, so that's something which we can consider as given. Now, next thing is, let's consider there is certain process which we observe in this particular system, And this process is changing, basically, its object, if you wish. It's changing its coordinate, which is x, and obviously the time also is changing. So it produces certain trajectory in this particular system. Now, coordinates which we mark capital X and capital T in this particular coordinate system are describing position at time of this particular object in this system. Now, how about an observer which is sitting in this particular system, which is moving, and observes exactly the same process? Well, obviously, whatever coordinate x and t were in this coordinate systems will be different in this, because this system is moving. So the question is how, based on just this information that this system is moving relatively to this system with a constant speed v, how the coordinates will look in this system if you know coordinates in this system. Classical Newtonian mechanics actually says very simple. Time is exactly the same. And as for space coordinate, so if this thing has coordinate x, then this system, the coordinate of the same point in this system would be minus vt, right? Because this system is moving, so at time t it will move by this particular distance. So if you take this particular point at time t coordinate x in this particular system, in this it will be x minus vt, because the whole coordinate will move relative to this one by the amount of vt. So this is a simple Newtonian approach. Well, great, but now we had a very interesting observation, which was physical observation, the experiment of Michelson, which actually says that measured in both systems, moving and standing still, speed of light is exactly the same. Now, it's impossible in the Newtonian sense, because in this particular case, speed, which is actually the ratio between the increment of the distance divided by increment of time, obviously the speed would be different in this particular case, and the difference would be v. However, if you measure the speed of light in both systems according to the experiment of Michelson, speed moves with exactly the same speed. Light moves with exactly the same speed in both systems, and somehow it means that these equations, well, either they do not reflect the way how light is actually moving, they are not universal, or we have to, change equations to make them universal. And that's exactly what Einstein did. He came up with a different transformation formula, not this one, but different one, which, if used, it will actually show that really speed of light moves with exactly the same, is exactly the same in both systems, standing still and moving. And that's what I would like actually to derive using the systems of linear equation. So, I don't have this, but what I do have is that there is certain object, which is light in this case, but it doesn't really matter from the mathematical standpoint. There is certain object, speed of which is exactly the same as measured in both systems. This is another, like an axiom, which I would like to add. So one axiom is that the system lowercase xt is moving with a constant speed v relative to this one. And the second axiom which I would like to add is that the speed of some object is constant, it's c, and yes, physical essence of this object is light, but it's irrelevant. So there is an object which has a constant speed as measured in this and in this coordinate system. All right, so that's given. Now let's talk about mathematics. First of all, we obviously assume that at moment t, which is equal to 0, both coordinates are at the same place at the same time. So in the beginning of the time, we have both coordinates at the same place, which means that if t equals to 0, then and x equals to 0, which is the coordinate system, at this moment, lowercase x, t and x both are equal to 0. That's what it means that both systems coincide at moment t. So this is also a given thing. It just makes our life easier. What else I'm looking for? Well, I'm looking for transformation of coordinates, not the ones which I have just written, which are Newtonian transformation, which we know are not true for life, but some other transformation. So basically, from purely mathematical standpoint, I would like to write a transformation of this kind, a linear transformation from x, capital X, capital T coordinates to lowercase x and t coordinates. So from constantly positioned, from a standing still coordinate system, transformation into the coordinates of the moving system. And that's what basically we are looking for. Now, in the elementary case of Newtonian mechanics, as I was saying before, t is equal to capital T and lower x is equal to capital X minus vt. But in Einsteinian mechanics, in the theory of relativity, where the light has constant speed c, we are looking for something else. And now our problem, actually our task, is to find these coefficients. Well, first of all, because of this condition, if capital T is equal to 0 and capital X is equal to 0, then the lower T and X are equal to 0. So the systems coincide at the very beginning. What follows is that these are equal to 0. So we don't have these free constants. That makes our life easier. So we're looking for this particular system. Now let's think about what kind of conditions on P, Q, R, and S we can impose to basically find these values, and that what actually will constitute the transformation of coordinate. So we are dealing with a problem of finding 1, 2, 3, 4 unknown variables. And for these 4 unknown variables, I would like to put together a system of linear equations, the result of solving which would give me these coefficients. And that's what actually is needed. And that's where the mathematics of it will fit. All right, so we know what we want to find. We don't need these pictures anymore. And if we will, I will draw it again. So let's think about what kind of equations we need. Now, there is some piece of knowledge which you might not actually be familiar with. It's a very simple one, and it's very simple to formulate. It's a little bit more involved to basically explain, and maybe in some further lectures I will dedicate a certain amount of attention to this particular principle. The principle is as follows. You see, we are transforming coordinates from one system to another. But we don't want something like, let's say, the distance between two different points to be different if I measure it in this system rather than in that system. Now, as a consequence of this, we will probably don't have, let's say, angles to measure differently in one system versus another. Because these linear transformations of coordinates can be stretching, can be changing the position, etc. So I don't mind to change the coordinates in some way, except I don't want the distance between the points to be measured differently. So if I will measure distance between 2 points, let's say capital X1 and capital T1 and capital X2 and capital T2, and then I measure, based on this transformation, the corresponding coordinates in the moving system, lowercase x and t, I would like to have the same results. How can I achieve this? Well, there is a very simple rule, which it's called orthogonality of the transformation. So transformation should be not deforming. And the criteria, if you have an equation, system of equations like this, to transform coordinates from one to another, is very, very simple. It's p times s minus q times r is equal to 1. I don't want to get into why I know about this. There is the whole theory of this. It's known, it's established, well established in mathematics, and I realize that you might not know it. However, just take it as at face, basically, that this criteria is the one and only criteria which is needed for this transformation to be non-deforming. And this actually constitutes my first equation. I have to say this is not a linear equation, but nevertheless, there are others will be a little bit better. But we are looking for linear transformation of the coordinates. Now, we've got this particular equation. That's one. We have 4 different variables, so we need 4 equations. All right, let's continue. Okay. Now, let's think about this. Since one coordinate system is moving relatively to another coordinate system at constant speed v, then let's think about what happens at moment t. So this is our first equation. Second equation. Let's talk about moment t, and x is our coordinate, and I'm looking only about point which has a coordinate x is equal to 0. So what happens with this particular point? What exactly are coordinates of this particular point in the moving system? Well, if moving system is moving at the constant speed v, it means that this point, which is the beginning of coordinates at moment t, would have coordinates like this. This is 1. This is another. So these are x and t. These are x and t. So what is coordinate of this system? Well, at any moment t, its coordinate along the x is 0, because it's the beginning of the coordinate at any moment t. Now, what is this particular coordinate relatively, this particular point has coordinate in this particular system? Well, since this is moving with a constant speed v, at the time t, it will be on the distance vt from the beginning. Speed times speed multiplied by time. So, what I would like to say that this particular point has coordinates t0 in this coordinate and capital T vt in this coordinate. So what does it mean? It means that our transformation, and let me write down again our transformation here. So we were talking about x lowercase is equal to px plus qt, and t is equal to rx plus st. So if I substitute, instead of t and x, I will substitute these, which are the time and coordinate of the 0 point of the moving system. In the moving system, I will get t and 0. So let's just, substitute it, and what we will have. Instead of x, I will put vt. Instead of t, it will be t. And so instead of this x, it will be 0. And instead of tt. So my system would look like this. Z is equal to p vt plus qt, and t is equal to r vt plus st. Now, this is something which I don't really need right now, but I do need this. So I just factored out t. But now let's think about this way. This is supposed to be true for any time moment t. How can it be done only by having this equals to 0? Since t can be anything. And this constitutes my second equation. So pv plus q is equal to 0. This is my second equation. pv plus q is equal to 0. This is my second equation. And again, this equation I basically derived based on the fact that the moving system of coordinates has a beginning with lowercase x coordinate 0. And the same point in the non-moving system has x coordinate as vt, because the v is a constant speed at which it's moving. And from this, I have derived this particular equation. Now, next. Now, let's remember this speed of light being the same in both systems. It's a very interesting consideration. What is the speed of light in the moving system? Okay. If I have an object which is moving in the space relatively to the moving system, its coordinate will be t and ct, right? Always. So at any moment t, if we started actually, if this particular object, a ray of light, started from the beginning of the coordinate, then at time t, it will be on this distance from the beginning of the coordinate. Now, what will be its coordinates in the system which is not moving? Well, that would be its coordinates. Because it's exactly the same thing, exactly the same speed. The time would be capital T, and the distance it will travel be c times t. So what's interesting is that this particular and this particular coordinates, one in the moving system, another in the system which stands still, are supposed to be related by the same original equation. So that's basically what I wanted to say. So if x is equal to capital Xt, lowercase x is equal to this. So now let's go back to our original system of equations, which is x is equal to px plus qt, and t is equal to rx plus st. Instead of x, we will substitute ct with a capital T, and we have to get ct with a lower t, because this is lowercase x. So we will have ct equals p, instead of x, ct, capital Ct, plus qt. And t is equal to r ct plus st. That's what we get. Now, I need the relationship between P, Q, R, and S, right? So, what I will do, I will substitute this T instead of this. And what I will get C times this thing, which is R C squared T plus SCT equals PCT plus QT. That's what I will get. And obviously, T can be factored out and reduced, so I will have RC squared plus CS is equal to PC plus Q plus Q. This right? RC squared, yes. So this is my third equation, which connects P and Q and R and S. We need four, right? We have four independent variables. Now, the fourth equation is exactly similar to the third one, but instead of light going from the beginning of the coordinates towards this direction, I will send the ray of light the opposite direction. Now, no matter which direction I will send the ray of light, its speed is exactly the same, and it's c, no matter what. But now the equation would look just very, very slightly different, because at the moment capital T, the position relative to this system would be minus ct, and the position relative to this system would be t minus ct. So this coordinates are transformed into these coordinates. And we will use exactly the same approach as before. Lowercase x, which is minus ct, is equal to p, capital X, which is minus ct, plus qt. And t is still r minus ct plus s. Now, substitute this t into this. What do I get? I get minus c times this. So it would be minus c times this. It would be minus rc square t. Then minus sct equals minus pct plus qt. That's what I will get. Now, again reducing by t, I will get rc square minus sc equals minus pc plus q. This is my fourth and the last needed equation. Now c is a constant, so I have everything here which is needed to find p, q, r, and s, because everything else, c and v, are constants. So all I need is to solve this system of equations, which by the way is relatively easy, and I'll show you how. These are linear, and these are linear. So three linear equations, except one has the power of 2, basically. So the way how I will solve it is, for instance, I can express this q as a function of p. Q is equal to minus pv, and substitute it into this and this. Well, before doing that, I can actually eliminate something. So let me add and subtract these two together. If I will add, my SC would disappear, and my PC and minus PC would disappear, right? So I will have RC square equals Q. Well, actually 2RC square equals to 2Q, but I will reduce by 2. Now, if I will subtract from this, I will subtract this. Now my RC square and Q would disappear, but what is left would be SC and PC. So SC equals to PC. Which basically is S is equal to P. Now I can use this, substitute it into this, and I will get minus PV. And what do I have now? I have Q, R, and S, all expressed in terms of P, and I can substitute it into the first equation, Q, R, and S. And I will get basically a second degree quadratic equation for P. Okay, let me try. I hope I will not get lost in these calculations. So instead of s, we can put p. So it's p squared minus qr, q and r. So q is minus pv, r is minus pv divided by c squared. And that's equal to 1. So this is a quadratic equation which gives me the value of p. Alright, let's try to solve it. So we have p squared minus minus and minus, so it will be still minus p squared v squared divided by c squared equals to 1. Am I right? Looks fine. From which p squared equals to 1 over 1 minus v squared c squared. So I factored out p squared. I have 1 minus v squared over c squared, and then I divided 1 over it. So p is actually a square root of this. All right. Now, if I know p, I can basically find all the rest of these. So I don't need this anymore, I hope. And I'm basically ready to write down the transformation. X is equal to p capital X. So instead of p, I will put this. So it's p divided by this plus q plus qt. Now instead of q, I will put minus pv. Oh, this is x, obviously, and this is t. Minus pv divided by same no, I'm sorry. Instead of p, I have to, instead of q, I have to put this. So instead of q, I have to put this. Now, so it's v over this. Right? So I can put minus here. And I think this is the formula. Or I can factor out. No, I don't need this p. This is 1. Right. Okay. That's what it is. Right. So p is 1 over this x plus q, which is v over this with a minus sign and t. Right. That's the right way. So what I will do here, I will do it this way. It's a common denominator, so I will put it here. X minus vt on the top, and I will have this. That's my transformation of x. Now, transformation at time. By the way, speaking about transformation of x, if you remember, Newtonian mechanics had only x minus vt. Now, the Einstein's relativity theory adds this particular multiplier. And that's what actually makes the whole thing different. This quotient, this factor, multiplier, is a hallmark of a special theory of relativity. That's what makes speed of light the constant. Now, about transformation of time. Well, in Newtonian mechanics, time is absolute. It's not changing from one system to another. In this case, it does change. So it's Rx plus St. So instead of R and S, we will substitute its values. So R is minus PV over C squared. P is this. So it would be minus V over C squared and this multiplier. That's R, which is V over C squared minus and over this, right? Plus St plus S, which is P, which is the same thing. So it's T. And here we can say that it's T minus V over C squared. So it's T minus V over C squared times this same famous factor. So this is the answer to our problem. This is how time and space coordinates are transformed in the theory of relativity. Again, in the Newtonian mechanics we have only t. Lowercase t and capital T are the same, because the time is the same, absolute. In Einstein's relativity theory, this is a shortening of time. So the system is moving and the time is shortening. If you read some popular things about relativity theory, you would notice something like paradox of twins, etc., and that's actually what explains it. This is the reason, mathematical reason. So this lecture is basically an exercise in how pure mathematics can solve physical problem using a relatively robust and rigorous approach. I basically assume certain things about coordinate system moving relative to another coordinate system with a constant speed, and what's very important, the result of experiment made by Michelson that the speed of light is exactly the same whether it's measured in a constantly positioned system versus moving relative to this coordinate system. Now, out of these two, well, you can call it axioms if you wish, or prepositions. Everything else is derived purely mathematically, purely logically, without any kind of intuition, physical consideration, thinking, etc., etc. And these are the equations which exactly correspond to what Einstein derived in his famous article about electrodynamics more than 100 years ago, which was the beginning of the theory of relativity. Okay, so just an exercise in systems of equations. As you saw, my system of equations for P, Q, R, and S was almost linear. I mean, 3 linear equations and 1 quadratic. And that gives me a linear transformation of coordinate from one system into another relatively according to the relativity theory. There are notes to this particular lecture. They are at unizor.com, as usually, where all these prerequisites and calculations are listed. I do recommend you to go through these notes again. It will be just a nice exercise, and again, it's something which is a rare, in this particular course, a rare connection to some real life. It's not just abstract math, it's an application of abstract math to a physical problem. That's it. Thank you very much.